In this work, we pose a part decomposition issue for additive manufacturing. The main objective of this research is to develop an evaluation method for part decomposition based on standard guidelines. In this video, I'm going to address three research questions. First, what is the part decomposition for additive manufacturing and why this is important? Second, how to evaluate decomposed parts. Lastly, how to optimize the part decomposition. Part decomposition is the redesign process of decomposing an original model into sub-assemblies. Why do we need part decomposition for AM? There are mainly three reasons here. First, to fit in a limited build envelope. To build a part that is larger than a 3D printer, it should be decomposed. Second, to reduce build time and cost. By decomposing a part, we can avoid support structure and reduce build height. That could cause more time and cost. Lastly, to improve surface quality. By decomposing and changing build orientations, we can reduce the stair-stepping effect that is one of the main reasons causing poor surface quality in AM. Let's say now we do the part decomposition for AM. At this moment, what should we consider for the part decomposition? Basically, the decomposed parts are built by a 3D printer and then assembled back after a build process. Therefore, when addressing part decomposition, we should consider a variety of factors that affect build and assembly processes. In particular, the geometry of decomposed parts is critical in failures, defects, inefficiencies, or feasibility for both processes. In this study, we mainly focus on the geometry of decomposed parts affecting build and assembly processes. To provide a more general perspective, we refer to a design standard document for AM. The standard document includes 8 categories for design considerations. In this document, we selected 8 design considerations associated with part decomposition from the product and geometry categories. Then, to quantitatively evaluate the design considerations, they are formulated as mathematical forms. We name this as evaluation indicators for part decomposition. Now, decomposed parts are evaluated based on these indicators. Let me explain one of them. Concavity. It is the volume of concave spaces. This indicator can be used to recognize multiple design considerations. Concavity refers to a measure for concave features, such as sunken edges, hollows, and holes. Usually, the concave features cause support structures, and this issue can be solved by part decomposition. To recognize the concave features on 3D models, we define concave spaces, which is the remaining spaces after subtracting the original model from its convex hull. A convex hull is the smallest convex envelope that contains a certain model. In the mathematical equation, it can be calculated by subtracting the volume of parts from the volume of convex hull. From now on, let me show you how these indicators can be applied to the optimization of part decomposition. To implement part decomposition, we applied VHACD, that is often used for collision detection in video games and computer animation, invented to reduce computational complexity. The evaluation indicators applied to optimize the decomposition outcome of VHACD. For this optimization, we adopted a genetic algorithm. When using VHACD, we set 12 input parameters. The decomposition outcomes depend on how to set these input parameters. There's a part here. This part has some holes around base plates and a NIST logo. Let me show you how this part is decomposed by VHACD. Here are the 12 input parameters of VHACD. The decomposition outcomes depend on how to set these input parameters. If we change the values for these parameters, a decomposition outcome would be different. Now we set these parameters as default values and run this algorithm. After VHACD, we got 17 decomposed parts. But when you see this outcome, you might feel a little uncomfortable because this geometry is way different from the original one. The small holes are gone and the NIST logo is disappeared. If you're a manufacturer, you never want this situation. Why this is happening? That is because the VHACD algorithm provides convex holes as output decomposed parts. To deal with this, we added a follow-up process after VHACD to keep the original geometry. But still, you might not like this decomposition result since it is over-decomposed. There are too many pieces. It seems like some parts do not need to be decomposed in terms of manufacturability. Therefore, we need to optimize the part decomposition by the genetic algorithm. In the genetic algorithm, the chromosome structure is comprised of the 12 input parameters of VHACD. When we change the input parameters, the gene is changed, which results in a different decomposition outcome. And then the decomposition outcome is evaluated by the evaluation indicators we developed. The evaluation results for indicators are summarized into a fitness function for the genetic algorithm. If the algorithm reaches to the maximum generation, it is terminated. Otherwise, it keeps doing this procedure with crossover and mutation for a new generation. Now let me show you the optimization result for this part. As you can see, we got only 5 parts. Also, this decomposition more makes sense than the previous one. Even if someone who is not a computer caught it, it could have been the same result. In the G-based optimization, we look for the optimal combination of the input parameters of VHACD to minimize the fitness function. In this example, we prepared a 3D model that is larger than a 3D printer. Therefore, feasibility is infeasible, which means that a part is larger than the limited space. After part decomposition, we can make the decomposed parts smaller, which is feasible for feasibility. There is a trade-off among the evaluation indicators to minimize the fitness function. Therefore, in the middle of optimization, If some indicators get large, others get small. After the optimization, roughness and overhang became large, while interface and quantity became small. Additionally, we compared our optimization approach with a similar study that applied VHACD. As you can see, the geometry of original models is maintained in our approach. This could be critical in lattice and honeycomb structures. When we compare material consumption between the two studies, our approach can save a lot of input material. Thank you for listening.